Imagine standing on the edge of Earth's deepest abyss, looking into the crushing darkness. Now, imagine if all that water disappeared entirely. Looking at this map, we can see the sheer geographic scale of this feature. The Mariana Trench is a massive crescent-shaped depression, stretching roughly 2,550 kilometers across the western Pacific Ocean. In this diagram, we see how extreme the depth of this scar really is. It plunges nearly 11 kilometers into the crust. You could take Mount Everest, flip it upside down, and it would easily fit inside, with kilometers of room to spare. Right now, this entire deep ocean system is locked under an immense physical burden. The water column exerts a localized hydrostatic pressure of up to 110 megapascals at the seafloor. That's over 1,000 times the standard atmospheric pressure you experience at sea level. Stripping away that massive water column instantly shatters a delicately balanced thermodynamic and geological system, triggering a cascading collapse of the local environment. If we were to walk down the exposed trench walls, the ground would immediately fail beneath our feet. For millions of years, these steep sediment slopes were physically supported by the surrounding water. Without it, massive sections of the canyon wall give way, creating immense landslides of falling rock and debris. This diagram shows a subduction zone. The dense Pacific plate constantly thrusts underneath the lighter Mariana plate. Without the water weight, this pressurized fault line unclamps. The plates slip violently, setting off megathrust earthquakes along the entire 2,550-kilometer boundary. Continuing our descent through the tremors, we would find a landscape that looks like a ruined alien city. The seafloor here is dotted with towering hydrothermal vent fields and massive mud volcanoes. These geological features are about to undergo a process called volatile exsolution. Magma stored beneath the crust contains huge amounts of dissolved gases, primarily carbon dioxide and sulfur dioxide. Under extreme water pressure, those gases remain safely dissolved in the liquid rock. When you remove that confining pressure, those dissolved gases rapidly expand into bubbles. At vents that normally release liquid carbon dioxide, the sudden pressure drop causes the fluid to flash instantly into explosive plumes of gas. Nearby, convective pools of liquid sulfur violently boil over, ejecting toxic sulfurous ash into the surrounding air. The trench's geology is essentially a volatile, unexploded bomb that relies on the immense weight of the ocean as its safety pen. Down on the muddy floor, the immediate aftermath leaves a bizarre array of Hadal zone megafauna stranded in the open air, including 6-foot-long giant tube worms and swarms of pale, blind amphipods. This is also the hunting ground of the Mariana snailfish. As an apex predator of the abyss, it has evolved over millions of years to thrive in absolute darkness and near-freezing temperatures. But the biology of these deep-sea creatures contains a fatal paradox. They don't simply tolerate extreme pressure. Their internal cellular machinery structurally requires that crushing weight to function. Inside the cell, a chemical called TMAO forms a protective shell around vital proteins, keeping them operational against the crushing ocean weight. When that external pressure is removed, TMAO overstabilizes. The proteins lock into rigid clusters, and the cell membranes instantly rupture. Exposing these highly specialized organisms to normal atmospheric pressure causes an instant, microscopic biological collapse. The animals don't suffocate. Their very cells dissolve, reducing the bizarre leviathans of the deep into disintegrating matter right before our eyes. Looking at this topographic map of the trench axis, we finally reach the absolute bottom, a series of steep valleys known as the Challenger Deep. As recorded in this research abstract, the deepest basin bottoms out at exactly 10,935 meters below mean sea level. You might expect the bottom of an 11-kilometer hole blocked from the sun to be a freezing, quiet valley. Instead, the newly drained Challenger Deep transforms into a superheated atmospheric oven. This diagram illustrates what happens when the water vanishes. Earth's atmosphere immediately rushes down to fill the 11-kilometer void. As the air sinks, the sheer weight of the miles of atmosphere above it forces the molecules to pack tightly together. This intense physical compression triggers a process known as adiabatic heating. Sinking air is squeezed so forcefully by the surrounding pressure that its temperature skyrockets, completely independent of any external heat source like the sun or magma. At the bottom of the Challenger Deep, the localized air pressure triples to roughly 3 times the standard atmospheric pressure. Driven by that extreme compression, the ambient temperature at the bottom of the dry trench reaches a baking 132 degrees Celsius, or about 270 degrees Fahrenheit. The massive accumulation of decaying Hadal biomass, scattered across the fine clay of the seafloor, literally cooks in this pressurized heat. As the organic matter rapidly breaks down in the hypoxic air, it releases thick, lethal clouds of hydrogen sulfide, methane, and ammonia, trapping toxic gases deep inside the canyon walls. The Mariana Trench functions as an interconnected machine of pressure and cold. Its biology and geology exist only because of the stability provided by the Pacific Ocean. Without that weight, the abyss rapidly and violently destroys itself.